Hello, my name is Rusty Bascom. I am an engineer with a local engineering consulting company based in the Rotterdam-Schenectady area. I understand that you may have an interest in a career in engineering, so I'm hopeful by sharing some of my experiences, both with attending college and in my working career in the last 30 or so years, you may be able to make some better choices about how you might like to proceed with your education studies, both at Mahonison High School and by attending universities after you graduate from high school. During this presentation, I will give you some background on my educational studies as well as my professional career, and also hopefully provide some guidance on the different types of engineering that you might want to pursue. A career in engineering can be very rewarding, and there are generally many employment opportunities in this field of study. With respect to my educational background, I graduated from Albany High School in 1985, and then I attended Hudson Valley Community College in Troy, New York, where I studied engineering science. After Hudson Valley, I transferred to Rensselaer Polytechnic Institute, also in Troy, where I earned a Bachelor's of Science and a Master of Engineering, focused on the area of electric power engineering. I started my working career in May 1990 after graduating with my master's, and I began working at a company called Power Technologies Incorporated located in Schenectady. After that, I joined a small engineering consulting company called Power Delivery Consultants, where I worked for 9 years. And then I co-founded my own engineering company in 2010, where I continue to focus on the area of electric power engineering and a specific area related to underground power cables, which I'll talk about later. One concern for any type of college education is the cost. I attended Hudson Valley Community College, and at the time, the cost for a year of education there was around $1,300. At the same time, RPI had a cost of around $13,000. So the Hudson Valley tuition was roughly 10% of the cost of attending RPI. An advantage of attending Hudson Valley Community College was I was able to transfer to RPI as a full junior, and I was able to complete my education, my bachelor's degree, within 4 years. At the same time, I had saved roughly $24,000 by going to Hudson Valley for the first 2 years of my school, rather than going to RPI. In 2021, the cost ratio is approximately the same. The cost to attend Hudson Valley Community College is just under $6,000, and the cost to attend RPI is just under $60,000, so roughly about the same 10% ratio. From the standpoint of considering the cost of education, Hudson Valley students may be eligible for the Excelsior scholarship, which provides tuition assistance to qualifying students, and therefore you might significantly save on the cost of attending college by going to Hudson Valley or another state university. SUNY Buffalo also offers various disciplines of engineering, and the cost is roughly $9,400 per year, plus the room and board. So there is the possibility you could attend Hudson Valley for 2 years and transfer to SUNY, or potentially attend SUNY Buffalo for 4 years and get a very good education while also saving money by taking advantage of the Excelsior scholarship. Interest in a career in engineering may begin in high school, where you should focus on subjects such as math and science, so that you're prepared to then study those subjects again when you're at university level focusing on engineering. One of the interesting parts of engineering is that the first 2 years of study at almost all universities is very similar. You'll be taking 3 or 4 classes in mathematics focused on calculus. You'll be taking 2 to 4 classes in physics, and you'll generally be taking 1 or 2 classes in chemistry. You will also take some very basic classes that most engineers take, including thermodynamics, some mechanical engineering classes, and basic electrical circuits. It's then after the first 2 years of study that you might start to see some more specialized coursework that focuses on a particular area that you might want to follow as a career. Some universities don't require that you select a particular type of engineering until after your sophomore year, because they recognize that the first 2 years of study are pretty much the same for all engineering students. After your sophomore year, you start to take courses that are more specialized in a particular area of engineering that you intend to pursue. Many colleges have some constraints on the number of students they can accept into each discipline, so some types of engineering tend to be more competitive for acceptance than others. This slide summarizes some of the types of engineering and also some approximate starting salaries for the various disciplines. There are many different types of engineering, And while you may focus on a particular technical area while you're studying engineering, you'll often find in your career that you're working in more than one engineering discipline to do the tasks associated with your particular job. Biomedical engineering is a particular field of mechanical engineering that focuses on either equipment or materials that are used for patients or treating patients. And it could include areas such as robotics or prosthetics that might be helpful in enhancing the quality of life for a patient. Chemical engineering is essentially applied chemistry, and there are many fields that utilize chemical engineers for the various processes that are associated with manufacturing of goods. For example, the case on your cell phone was probably developed by a chemical engineer to give it its properties to resist cracking and breaking if you drop your cell phone. And there would be some overlap potentially with the petroleum industry, where a chemical process is used in the refining of oil to make gasoline and other petroleum products that we use as consumers. Civil engineering is the oldest type of engineering and relates to the building of any kind of structures or facilities, generally for a community. Highway projects, roads, buildings, any type of bridges are generally affiliated with a civil engineer or civil engineering work. Electrical engineering is associated with any kind of electrical devices. It could include things like your cell phone, your computer, your television, toaster oven, washer and dryer, any type of device that uses electricity. Electrical engineers are also associated with the making of electricity, the transferring of electrical energy, and utilization of electrical energy. And it's actually my field of study. Environmental engineering has anything to do with managing and controlling the environment and could overlap with other disciplines such as biology, chemical engineering, and maybe civil engineering. Industrial engineering is associated with any type of manufacturing facility where there might be equipment used to control or manage processes. And it's the setting up and configuration of that equipment that is often the focus of an industrial engineer. Mechanical engineering is probably the broadest field of engineering because almost all types of engineering have some aspect of mechanical engineering associated with them. It could include anything associated with manufacturing, electrical energy, environmental engineering, civil engineering, structures, any type of activity related to a mechanical device or system. And so mechanical engineering has a very broad application in the field of engineering. Petroleum engineering is a specialized type of chemical engineering that is focused on the processes for extracting natural gas and oil for the use in the energy industry. You'll note that the different types of engineering also have a different associated starting salary. Part of the reason for this difference is the qualifications and education needed to work in these fields of engineering. Another reason for the difference is the environment and the conditions under which the engineer has to work. For example, a petroleum engineer might have to work on an oil platform in a foreign country or under conditions that are less favorable, and as a result, he or she might receive a higher starting salary because of those conditions. When considering the different types of engineering, you should think about what is of most interest to you rather than the starting salary. If you're interested in the subject, you'll be more successful and also have a happier and more rewarding career. As I mentioned earlier, I'm an electrical engineer. Specifically, I'm an electric power engineer, which means that I am focused on the production, transfer, distribution, and use of electricity. The production of electricity usually involves coal, natural gas, nuclear power, hydroelectric power, solar, and wind. There are many uses for electric power, including residential for houses and apartments, industrial for production and manufacturing of goods, commercial such as stores, shopping malls, banks, etc., and municipal purposes such as streetlights, traffic signals, and other services. The voltages of most electric power are in three different ranges. Residential or light commercial is usually 120 to 240 volts. This is the voltage that we see on our wall outlets in most of our homes. 480 to 4,000 volts is a common industrial or commercial voltage, and 2,000 to 35,000 volts is often used for municipal purposes. Most of my work is related to the transfer or distribution of electric power, and that can be done using overhead lines as shown on this slide. Distribution voltages often use wooden poles as shown on the left. Higher voltage transmission is done using towers and poles, as shown in the middle and the right of this slide. The voltages that might be used are 69,000 volts up to 500,000 volts, and in a few cases, 765,000 volts. My particular area of engineering expertise is related to the underground transmission and distribution of electricity. The photos on this slide show some of the types of equipment that are used for that purpose. The photos on the left show an underground extruded cable, and the photos on the right show a pipe-type cable. These are the two most common types of underground cables that are used in the United States. Part of my work is to help utilities such as National Grid or Niagara Mohawk select the cables to use for their particular needs. This includes selecting both the type of cable for voltage and also the amount of power or current that can be supplied by the cable system. And I will spend days and sometimes weeks evaluating the alternatives and then making a recommendation for the utility to use and eventually purchase for their project. I mentioned earlier that when we get a degree in engineering, we often end up working in more than one engineering discipline. In underground power cables, I sometimes work with electrical engineering, which is where I have my degree, and I look at how electricity will flow through conductors, how magnetic fields might be produced by underground power cables, some of the aspects of electrical stress, and some of the ways that electrical equipment may fail. I also work in the areas of mechanical engineering because I have to know about heat transfer and how heat is going to escape from the power cables when they're buried underground. And last, I sometimes have to consider civil engineering because the cables themselves have to be buried in the ground in a way that is suitable for construction and installation for a utility circuit. And because of that, I have to also know how underground utilities are installed and then work with the various agencies and contractors that know how to install these systems. While engineers do spend a lot of time using math and science to do calculations, most of my time is spent writing. So English language arts is a very important aspect of the work that I do. I have to write proposals, write reports, and explain the results of my analyses, and also request that I get money to do the work that I do. So communication and writing is a very important aspect of being an engineer. In my work on a new underground cable project, where I'm often helping a utility design the cable system and buy the equipment, I initially perform a bunch of design calculations and coordinate with the civil engineer on how the circuit might be installed along city streets or between two locations, usually called substations. I then prepare a report with the results of my analysis. I also prepare specifications for the utility to use, which tells them what material to procure and how the equipment needs to be tested when it's manufactured. These specifications will also tell the utility on how to hire a contractor to perform the installation of the equipment. And lastly, I would be involved with providing quality assurance to make sure the equipment is manufactured correctly in the factory and also to be out in the field during construction to make sure the equipment is installed appropriately. Other work that I do includes failure investigations, evaluating operating and maintenance issues, and providing training and courses. There are many fun things about being an engineer that don't involve sitting at a desk. One of the fun things that I especially enjoy is going to a factory where I get to witness tests on cable before it's shipped to a customer. This particular slide shows some photographs from some of that laboratory testing. The photo in the top center is where they're actually manufacturing the cable and putting a plastic jacket on the outside of the power cable to protect some of the inner layers. The photo on the left is showing a test on the plastic jacket after it's been manufactured. They're stretching it to see at what tensile strength it actually breaks. The photo on the top right is where they've put a section of the power cable in hot oil and are heating it to see that there's no defects in the insulation material. And the photo on the bottom right is a high voltage test on the power cable. Here they're applying a very high voltage, higher than what the cable will normally see when it's put into operation, to make sure it doesn't break down or fail. And the advantage of doing this test in the laboratory is it's in a controlled environment before the cable is put into operation, and where it can cost the utility a lot of money to make a repair later. One of the fun activities I get to do as an electrical engineer is watch the cables get installed. This slide shows some photographs from different types of installations. The two photos on the left are installing cables in a buried installation, where the conduits are put into the ground ahead of time, and then the power cables are pulled into those conduits. The advantage of putting the cables in conduits is if there's a failure later on, the cables can be pulled out without digging the ground again. Other types of installations involve putting cables directly in the ground, and if a failure occurs, they have to find the exact foot of cable where the failure has occurred before they can make a repair. The photos on the right are showing the installation of submarine cables. Here, the cables are transported to the location where they'll be installed on a barge, which is the photo on the top right, and then the cables are lowered into the water using a special equipment that embeds the cables in the water bottom. This protects the cables and allows that they don't move once the installation is complete. As the responsible engineer, one of my activities is to oversee the installation of the equipment to make sure it's done according to the specifications that I've prepared and provided for the utility. After the cable segments are installed, the segments have to be spliced together in underground vaults or manholes. That's the photo shown here on the left. The cables also have to be connected to other equipment within a substation, and that's done using terminations. The three photos on the right show various types of terminations being installed in different locations, where they can then be connected to overhead lines or other substation equipment. Most underground power cable projects involve several years of activity. Initially, the utility will do some planning studies to evaluate if they need a cable system. Then the design may take 2 to 12 months, depending on the complexity of the project and the length of the project. After that design process is completed, they have to go out for bid to obtain the materials and the installation services to actually install the cable system. And that can usually take 1 to 2 months. The manufacturing of the cable usually takes 3 to 6 months, but could be longer for very large projects. And then the cable itself has to be shipped from its manufacturing facility to the location where it's going to be installed. There are some manufacturing facilities in the United States, but they also may come from overseas. So this can add time to the shipping process and the delivery of the equipment. The construction itself can take months to years. The entire trench must be excavated and the conduits must be installed ahead of time, and then the cables can be pulled into the ground. Some of those activities can happen simultaneously, but it is usually a several-month process as a minimum. The electrical installation then follows the civil installation, and that again can take several weeks and maybe months. And then lastly, when all the equipment has been installed, there's a commissioning process where the cables and the entire cable system are tested to make sure that they've been installed correctly and they will function as intended for the utility client. I hope this presentation gave you a high-level overview of the educational requirements to become an engineer and some of the options that may be available to you as a graduating Mahonison student. Also, I hope you'll consider reaching out to me during the virtual event that Mahonison will be hosting this coming May. During that event, I'll be able to answer questions live through chat. Also, if you have any follow-on questions, please feel free to reach out to your Mahonison guidance counselor for additional information. Thank you for listening.